Alright, welcome back. We got a launcher, we got a ball, we got tape, the black paper, and then we're gonna get white sheets. We're gonna lay them out, and we're gonna test where it lands so we can know where the theoretical is. And then we'll just put it there, and then we'll see where the black paper as it hits is gonna mark it. We'll see how much percentage we have, and that's about it. And then we're gonna put out different angles. Right now it's at 0, and then we're gonna do, what is it, 20?
No, I'm gonna do 0, 30, 45, and 60.
That's what I meant.
Yeah. Test 1.
I want to go get the ball.
Right. We're launching at all different angles then? Next one's 30. Yeah. Next 30. Yeah. 45. And then the last one. Yeah. Last one is 60. Okay.
The one that just marked.
Yeah, we need to do that 5 times so we can average to get the average of it. He has the ball.
Nice. I want you to write number 1.
Okay.
That one was a test. Just so we know. Then we don't like think like it's something else. Push it like 1 time. Just so I get the first time. Recorded? Where you got it, guys?
Can't scoop. That's the third one. When you say that's the third one.
This is 3. Yeah, this is 3. Zero. Wait. Okay. I'm supposed to wait. This is 5th one.
Measuring them.
We'll use those same videos. What are the degrees? Number 1.
Number 1 for it.
It's pretty consistent. I don't know why that scared me when you did that. Can we trade Rudy? Is that the best I can? What was that? This is 4?
Yeah.
They all hit like close as fuck to each other. Two's still not getting it. That's good. But then that does it. Doesn't matter. So number 1. That landed off the paper.
It did.
It did. How many is that?
This is 5 now?
Four. This is five. Six. Damn, that barely landed on the paper. Yeah, who would have thought it's going in a straight line? Yeah, we got. I forgot really good. Okay, contact. So let's test one. Now. One. Hands off.
You see what I'm telling you?
That is the.
Oh, yes, it's me.
Maybe download it before. Sit. Break. Four.
Here we have all of our numbers for lab 6. We start off with 0 degrees, measuring its initial and final position in both the x and y coordinates with initial velocity. Then acceleration is only in the y coordinate with gravity. And we find our time, and from there we get our Vm, which is equal to Vx. Then we find a theoretical distance for 0 degrees. And we would do the same with the rest in 30 degrees, 45 degrees, and 60 degrees. You can see here on our charts, it's shown, our numbers are shown here. And from there, we find a theoretical distance with all of them in 30, 45, and 60. And then after completing the lab, we find our experimental differences. And after finding our experimental differences, we calculate our percent error for each one of the angles we tested, which happens to be for 0, it was right on the money. For 30, it was 69%, 45, 40%, and 60, 53%.
Hello, and welcome back to our lab 6. Here I'm going to be breaking down our percent error. Our percent error mainly comes from how we measure things. Even small mistakes in distance, angle, or time can throw off the results. There's also human error, like starting a stopwatch a little too late or misreading a ruler. On top of that, our experiment isn't perfect, and outside factors like air resistance can affect the motion. All these small issues can add up, creating the percent errors we can only see in our data. Now here's the key issue. Our formula assumes a perfect world. There doesn't account for real life factors like air resistance, which slows down the object. It also assumes the launch angle and velocity are exact, which is rarely true in the experiment. Friction and energy loss are also ignored. Because of this, the theoretical values do not perfectly match what we observe, leading to noticeable differences in our results. What this tells us is that the percent error isn't just a mistake, it's actually useful. It helps us understand the limitations of our formulas and shows how real-world conditions affect motion. By recognizing these differences, we can improve how we measure and even adjust our experiments in the future.
These factors are not included in the formula and can cause differences in results. If the percent error is large, then these factors are significant and had a strong impact on the experiment. If it is small, then their effect is not very significant.
Do we think there's a way to minimize percent errors? Yes. By running the same simulation multiple times, we can see small changes that could cause these errors. The error flow, the timing between the release of the experiment, or other such things. Other ways to minimize these errors could be by getting more exact tools and more exact things, eliminating human error, having something release the item and have that be your consistent basis, and not having to worry about human error and human timing. Another way to minimize those percent errors could come from simply doing the experiment over and over and seeing the different changes and taking some of the better numbers. Although some of them could cause higher percent errors, with practice and with better simulations, better tools, timing, and other such things, these percent errors can be minimized pretty quickly. Are all the percent errors equal? Why or why not? They don't equal each other, they're not the same number, but they are within the same range. With us testing it physically, setting the timer, setting the release, or doing other such things, we ourselves cause a slight difference. Since this slight difference is the same, because all of us are doing the same experiment, same person releasing the ball, same person doing the timing, same person doing the measurement. Although we do check each other's work, there is slight deviations and there is slight differences, causing the percent errors to be close to each other but not equal to each other. They could be in range between 5, 10, and 20% difference between each one, but the average doesn't jump very differently from each other. They are still the same experiment done by the same people, causing some, or if not close to the same percent errors.